Okay, so let's look at higher dimensional systems. Higher dimensional systems, we can actually solve these problems somewhat similar with the same techniques that we have developed in one dimension. For example, let's look at uh, let's look at first problem of particle in a square well. So let me call this as square 2D box. The square well is something, that word is used for something else in. So that means I have a two-dimensional problem. So this is v of x comma y, which is equal to, this is equal to 0 or 0 less than or equal to x, or y less than or equal to L, and infinity otherwise. That means we have something like an xy plane. So let's say this is your 0 to L. Okay, this is x and this is y, and this is 0 to L. So particle can be in this region, and everywhere outside this region, the particle is, the potential is infinity. Okay, so infinity outside, and inside it is 0. That means essentially particle is confined to this region. So particle is confined to 0L cross 0. Okay. Now you can see that if you write down Schrodinger equation, so we use Schrodinger equation in the following fashion. That is, for energy eigenvalues, we have to solve this equation, H psi is equal to P psi, where the Hamiltonian is given by minus h bar square by 2m into the kinetic energy operator del square plus v. In this case, it will be v of x comma y. So this is the Hamiltonian. But for two dimension, for 2D, we have this del square written in terms of del square by del x square plus del square by del y square in Cartesian xy coordinates, as we have. So this h psi is equal to E psi. Okay, so this equation takes the following form. So we know that in the region of interest, that is for 0 less than x comma y less than L, in this region. Okay, so in this region, v of xy is 0. So we have minus h bar square by 2m plus into del square psi. Psi will be now a function of x comma y by del x square plus del square psi of x comma y by del y square is equal to E into psi of x. So this is the equation. Now I can use something called it's a partial differential equation. So use this separation of variables. So this is a technique which you might have learned it in your efforts to solve partial differential equations. So that means I'm going to use this psi of xy as um, some p of x into some q of y. Okay, and substitute in this, then you get minus, or you write this differential equation taking this on this side. Okay, so I can write this as I will do two steps. One is first substitute this. Then since this particular term is a differential with respect to x, your q will come out, q of y into d square p of x, because p is only a function of x, so I am writing d square p by dx, plus in the second term p will come out, and d square q of y by dy square, plus e in sorry, this is not e, but I would call this as mm, I would call this as k square, or I can simply call it as kx square plus ky square. Okay, into p of x into q of y is equal to. Okay, I could call this as simply k square, but I can say k. So this e now probably can be written as some ex plus ey. This is not component, but it is, there is some energy along for the dynamics along x-axis and some energy along the dynamics along y-axis. Okay, so here what do we understand is that here this ex is equal to h bar square kx square by 2m. Similarly, ey is equal to h bar square ky square by 2. Now you can write this. So divide this, this is the next step. So divide by p of x into q of x, q of y. Then you will have 1 by um, yeah, so let me write this in the following fashion. 1 by p of x into d square p of x by dx square plus 1 by q of y to d square q of y by dy square plus so I could have written this. So let me simply write this as k square in k square. Now p of x and q of y both will go to 0. This is equal to 0. Now this is a constant. Okay, so this is constant. Okay, so this is only a function of x, and this is completely a function of y. So you have a complete function of x and a complete function of y, which is equal to minus k square. Okay, so I could call this as some kind of minus kx square plus ky square. Okay, so if I take this to the other side, this is equal to minus kx square minus ky square. Okay, now you can see that this is basically like two different equations. Okay, so we have two equations. We have two equations, basically differential equation. One equation is d square t of x by dx square plus kx square into p of x is equal to 0. This is one equation. Remember, this equation is exactly like a particle in a one-dimensional box equation. And then you have another equation, d square q of y by dy square plus ay square into q of y is equal to 0. So these two are similar equations. I mean, basically mathematically same equations. So, and now onwards I don't have to do, because this is something which we have done in one-dimensional case. So, based on the boundary condition that this p of x should go to 0 as x goes to 0 and x goes to L, the boundary condition. Same thing is true with q of y, should go to 0 as y goes to 0 and y goes to L. So these four boundary conditions are, if you put them, then what you get is uh, the energy, the total energy, which now depends upon two quantum numbers, namely nx and ny, will be equal to h bar square pi square by 2ml square into nx square plus ny square. Okay, so this is the energy eigenvalues. This actually we can read out from our earlier understanding of one-dimensional box. Okay, so this is just sum of the energies corresponding to two one-dimensional boxes, nx square plus ny square. And we could have also written this wave function. Also, we can read out of x comma y is equal to, now I will have something like 2 by L, one square root of 2 by L for x and another square root of 2 by L for y. 2 by L sine nx into x, nx pi by L into x, and sine ny pi by L into x. So these are the wave functions. These are the wave functions. Now the problem is completed. I mean, we have exactly solved this problem of a particle in two-dimensional box. Now you can see that there is nothing that we have done. We have simply used our
Excuse me, sir.
yes,
So it is sine ny pi y by L.
yeah. Sorry. So n y pi by L into y. Okay. So this is we have actually banked on our experience of one-dimensional problem, and this is fine. Now there is one feature that so let me just generalize it. So in three dimension, for example, in 3D box, that means we will have a cube, a cubic box of side L. That means it is, the particle is confined inside this cube. It cannot go out of this cube. In that case, your energy will depend on three quantum numbers: nx, ny, and nz. And the energy eigenvalues are h square by twice ml square into nx square plus ny square plus nz square. Similarly, your wave function nx, ny, nz which will depend on x, y, z, is equal to 2 by L to the power 3 by 2, 2 by L to the power 3 by 2 into sine nx pi by L into x into sine ny pi by L into y into sine nz pi by L into z. So these are the energy eigenvalues and energy eigenfunctions for three-dimensional particle in a three-dimensional box. Okay. Now we can ask, yeah. So we can ask, what is the? Is there anything that is some special feature that we will have to look at in higher dimensions?
Degeneracy, sir.
Yes. So there is something called degeneracy that is that appears in the higher dimensional systems. Okay. So let's try to understand what this degeneracy is. We talked about this earlier when we were talking about postulates of quantum mechanics. So the degeneracy is something like this. For example, if you take a particle in 2D box, particle in 2D box. So you know the energy eigenvalues are E nx ny is equal to h bar square pi square by twice m L square into nx square plus ny square. Now, if you take n is equal to 1, which is given by 2 h bar square pi square by 2 ml square. So this is basically the ground state. Now, what is the next energy? Next energy corresponds to 1 comma 2. So that is equal to nx square is, nx is 1. So 1 plus 2 square 5. So that is equal to 5 h bar square pi square by twice ml square. So this is your first excited state. Okay. Now, if you take E12 or E21, E21 is also same energy. That means there are two states. Okay. There are two states. For example, psi 12 of xy and psi 21 of xy. These two are different wave functions, obviously. So are two states with same energy. Same energy. Then we say that this energy E12 is equal to E21 is equal to 5 h bar square pi square by 2m L square is degenerate. And these are degenerate states. Okay, so in fact in this case is doubly degenerate. That means there are two wave functions corresponding to same so this kind of a degeneracy that is appearing is a characteristic feature of higher dimensional systems. Okay, so this is something which appears in higher dimensional systems, and we will talk a little more about degeneracy as we go along. But this is so degeneracy is usually something that appears in higher dimensional systems, and we have to deal with that. Okay. Now let us look at uh, another example that we have studied, of course, case P, namely a harmonic oscillator in 2D and 3D. Okay. Now, harmonic oscillator can be isotropic harmonic oscillator. Isotropic. What does that mean? That means omega is same for all dimensions. Maybe in all dimensions. And we can have something called anisotropic. Then in that case, omega is different. Different dimensions. So for example, let's consider 2D harmonic oscillator. So if your Hamiltonian is p square by 2m, so basically this is px square by 2m plus py square by 2m plus half m omega square into x square plus y square. Okay, that means this omega square x square and omega square y square. So this is isotropic harmonic oscillator. On the other hand, if you have Hamiltonian, which is px square plus py square by 2m plus half m omega 1 square x square plus omega 2 square y square. Then omega 1 and omega 2 are different. Then you have what is called anisotropic harmonic oscillator. Now, we don't have to really do this problem because we have already understood when you do separation of variables, etc., you can write them as two independent harmonic oscillators. So I can directly write down the energy eigenvalues. So energy eigenvalues of 2D harmonic oscillator. Okay, so this is something which I can write it down. So you have two. So now let me call this as n1 comma n2. These are two quantum numbers. That is equal to h cross omega into n1 plus half. This is for the first quantum. H cross omega into n2 plus half. So n1 and n2 are two quantum numbers. So this is for an oscillator in X. This is for an oscillator in Y. Energy is now because omega is same. So let us call this as isotropic case. Omega is same. I could have simply written this as h cross omega into n1 plus n2 plus 1. So this is what your n1 comma n2. So this is linear in n1 plus n2, and hence I can call n1 plus n2 as some n. Then in which case this becomes h bar omega into n plus 1 Okay. Now let's look at degeneracy. Okay, so let us use that notation. Let's say states can be denoted by a ket vector with n1 comma n2. These are number eigenstates. So let us denote them with n1, n2. So now let us write down uh, a tabular column where I give this n, a value n, and then what is your en, okay, and then the states that give rise to the same energy, and then what is the degeneracy. So if I take n is equal to 0, that means your E0 is h cross omega. Then what both n1 and n2 has to be equal to 0 because n is n1 plus n2, and n1 and n2 cannot be negative. So that is equal to the only state that gives you this energy is 0, 0. And that is the ground state. There is no degeneracy, so the degeneracy is simply 1. Now suppose if I take n is equal to 1, then I have 2h cross omega as my energy. Okay, but remember your n is equal to 1 by n1 equal to 1, n2 equal to 0, or n1 equal to 0 and n2 equal to 1. So that means I have two states here, 1 comma 0 and 0 comma 1. So these two states will give you same energy, 2h plus. So the degeneracy of this energy is 2. Now you take n is equal to 2, then this one is 3h cross omega, that is the energy. So n is equal to 2 can happen in 3 different ways. So you can have 2 comma 0, or you can have 1 comma 1, or you can have 0 comma 2. So these are the 3 different states corresponding to the same energy. So the degeneracy of 3 is actually, n equal to 2 is actually 3. Now let us write down one more, generalize that. So if I take n is equal to 3, then you have 4h cross omega, that is the energy. And now you can see that in how many ways you can get this 4h cross omega, because your n1 plus, so it has to become 3. That means you can have 3 comma 0, or you can have 2 comma 1, or 1 comma 2, or 0 comma 3. So there are 4 different states that give rise to same energy. So the degeneracy of this state is 4. Now you can see that you generalize this one. If you have some n here, that is, if some arbitrary n, then you are going to have you can have n comma 0 state, and n minus 1 comma 1, n minus 2 comma 2, and so on up to 0 comma n. So that means this n is starting from n, n minus 1, n minus 2, and goes up to 0. That means this will be totally, how many of them will be there? The degeneracy is actually n plus 1, because n and 1 to n is n, and there is a 0. So there are n plus 1 states. Okay, so this tells us that the degeneracy the degeneracy of nth excited state. Nth excited state of 2D harmonic oscillator is n plus 1. So this is a general formula that we have for this one. Okay. Yeah. Now we can think of three-dimensional harmonic oscillator. Okay. Three-dimensional harmonic oscillator. So let us look at 3D harmonic oscillator. 3D isotropic oscillator. Okay. So when you look at 3D harmonic oscillator, you will have what is called we have three quantum numbers. Okay, we will have three quantum numbers associated with three variables. So we can say that your energy n1, n2, n3 is equal to n1 plus n2 plus n3 plus every thing will give you a 0 point energy contribution of half. So 3 will be 3 halves into h cross omega. Remember, we're talking about isotrope. So I may call this one as n. Okay, so which is equal to n plus 3 by 2 into h cross omega. Okay. Now we would like to ask a question that, or maybe I will leave it for you as an exercise. Okay, exercise. Show that the degeneracy of nth excited state. Nth excited state right, state of 3D isotropic harmonic oscillator is I don't remember, maybe it is n plus 2 into n plus 1 by 2. So if I take 1 and 3, yeah, I think this is correct. So the n plus 2 into n plus 1 by 2. Okay. So if you are denoting Gn as the degeneracy of nth excited state, so Gn is equal to n plus 2 into n plus 1. Right. So maybe you can do anything. You can write down two different, a few different things, and then generalize it from there. Okay. So you adapt any strategy of showing this result. But this is the result, n plus 2 into n plus 1 by 2. So once you get this, then you can think of asking a question. Okay, three-dimensional harmonic oscillator is what we said, but then you can also ask as a means of continuation of this. So you can ask a question. Suppose if you have um, a d-dimensional isotropic harmonic oscillator. Okay. So consider a d-dimensional isotropic oscillator. Okay, this is for those of you who want some challenging problems. So d-dimensional isotropic harmonic oscillator, and find uh, Gn for nth excited state. So, and whatever general formula that you find here, uh, Gn, maybe I call it as Gnd. So in that case, this will be Gn3, and here you have Gn2 is n plus 1. So whatever general formula that you get, when you put d equal to 2 and d equal to 3, it should give rise to these formulas. So so you can try to find out this answer, and so this is kind of in textbooks you always see, that kind of 1-star problem, 2-star problem, like that. So this is in some sense a 2-star problem. So the difficulty level is slightly not very difficult, but you have to put in a little effort to think about this. So this is one exercise. Now, if you have, so the degeneracy will be lifted, or the degeneracy will not be there if you have an anisotropic harmonic oscillator. For example, if you take 2D anisotropic harmonic oscillator, 2D anisotropic harmonic oscillator, then your energy eigenvalues are going to be n1, n2. That is equal to n1 plus half into h cross omega 1 plus n2 plus half into h cross omega 2. Omega 1 is different from omega 1. So now I will not be able to combine this. Now, for example, you ask a question, what is, so let us try to make a kind of a table like this. Okay. So let's say so we will say the state and then the energy. Okay. So now let's assume that without any loss of generality, assume that omega 1 is greater than omega 2. Otherwise, it will be omega 1 will be less than omega 2. So one of them will be anyway larger. So I will call omega 1 is that larger. So if I take state 0, 0, the energy corresponding to this one is h bar omega 1 plus omega 2 divided by 2 with the 0-point energy associated with that. Now if I take 0, 1, okay, if I take 0, 1, then you will have h bar omega 1 by 2 plus 3 by 2 h bar omega 2. Okay, since omega is smaller value, then this one will have a smaller energy than 1, 0. 1, 0 will be 3 by 2 h bar omega 1 plus half h bar omega 2. So this energy will be smaller compared to this energy. So 0, 1 is the first excited state and 1, 0 is the second excited state. There is no degeneracy. Energy is different. So this energy is different from this energy. In the same way, if you have an anisotropic harmonic oscillator, then the degeneracy in all levels will be lifted. Okay, so it is only that isotropy harmonic oscillator we have degeneracy. Same thing is true in three-dimensional anisotropic harmonic oscillator. So the isotropy is important, okay, for emergence of this degeneracy in the energy levels. Okay, so this is one. So we looked at two classes of problems. One is started with particle in a box and then uh, try to look at particle in a box in higher dimensions, 2 dimension and 3 dimension, and then looked at the degeneracy. And there also, even in particle in a box problem also, if you take a rectangular box, that is, you're not taking a square box, but you take a rectangular box. Okay, so if you take rectangular box, so let me go and look at the energy eigenvalues that I had written here. Yeah. So the equivalent of this in the case of rectangular box, so rectangular box, that means your box is like 0 to L1 cross 0 to L2, because it's not same. Then what happens to these energy eigenvalues? E nx, okay, I call this nx comma ny is equal to h bar square pi square by twice m. You have nx square by L1 square plus ny square by L2 square. Now, since L1 and L2 are different, okay, since L1 and L2 are different, we don't have a situation that the ground state is same as the that 1 1 the, sorry 1 2 and 2 1 are not same. Okay, so let us say that L1 is greater than L2. Okay, so assume that L1 is greater than L2. That means what happens? Your 1 by L1 is smaller than this 1 by L1 is smaller than 1 by L2. Okay, so that means your L1. So now what happens in this E12 case? So whatever I'm writing in red is for the anisotropic case. So E12 case, you have h bar square pi square by twice m into you have 1 2, right? So that is 1 by L1 square plus 4 by L2 square. Okay, 1 by L1 square plus 4 by L2 square. 1 by L2 is a bigger number. So this energy is smaller than h bar square pi square by 2m into 4 by L1 square plus 1 by L2 square. Okay, so note that note that E2 comma 1 is smaller than E1 comma 2. Okay, and hence there is no degeneracy, and you will see that. So in some sense, the so L1 is equal to L2 is like this is an isotropic box. That is, we can say that L1 is equal to L2 is an isotropic box. If it is not equal, then it is an anisotropic box. Exactly in the same line of the language that we used in the harmonic oscillator case. Okay, so I have used these two examples.
Sir,
Yes.
so can I say that degeneration is a consequence of asymmetry in space?
Yeah. So asymmetry is basically is okay. You can say that of course, when you say you have an asymmetry, then you have to also talk about what is the symmetry. Okay, so now you can say that there is some connection between degeneracy and symmetry. So we have to understand what that is. Okay, so maybe I will make a few remarks about that. So we have something called. So what is the origin of degeneracy? So we can ask that question. What is the origin of degeneracy? Okay, so usually we say that one can relate. Okay, so whenever there is a degeneracy, okay, so degeneracy uh, implies existence of some symmetry. Okay, we may have to look for that. We may have to look for look for it. Okay, so uh, in general, we can make a forward statement more easily. Okay, suppose let's say there is a symmetry. Okay, so let's say that so let us say that we have a symmetry. Okay, we have a symmetry. That means there exists, there is an operator. Okay, so uh, that leaves the Hamiltonian invariant. Then we say that the system possesses that symmetry. Okay, so which means that I have some. So let's say that I have a Hamiltonian, and then there is an operator, some transformation operator, which I will call it as T, let's say, and T inverse H T. Okay, this is the transformation. Anytime when you say that Hamiltonian is transformed, it is this one, and that should leave the Hamiltonian invariant. That leaves the Hamiltonian invariant. Upon transformation, you will get the same Hamiltonian. Now this is equivalent. Suppose now I post multiply with T. Pre-multiply with T. Okay, so I get T times H is equal to H times T. Okay, this I will get on by pre-multiplying with. That means this statement is exactly same as, okay, something is leaving Hamiltonian invariant means that this Hamiltonian and then this transformation operator commute among themselves. HT is same as TH. That means their commutator is 0. Okay, so what does that tell you? Suppose let's say, so consider an energy eigenstate. Consider an energy eigenstate psi. with energy E. That means I'm having H when it operates on psi, it will be E psi. I'm not writing any particular sub-index here because this is a general argument. Now consider this T acting on psi. We don't know what this is. Okay, so consider this quantity. This is some state, right? This is some state. So let us call this as some phi. Okay. Now we ask a question: is phi? The logic is like what we did in harmonica. Is phi an eigenstate of H? So this is the question that we are asking. To answer this question, we operate H on phi. That is equal to, but what is phi? Phi is nothing but T acting on psi. But we know Ht is nothing but Th because H and T commute. So I can write this as T H on psi. But we already know H psi is equal to E psi because psi is an energy eigenstate. So this is nothing but E T psi. But what is T psi? T psi is phi. So that is equal to E phi. So I started with what is the action of H acting on phi. Then I came to a conclusion that it is E phi. That means the answer is that yes, phi is an eigenstate. Phi is an eigenstate of H with the same eigenvalue. E. What does that mean? That implies both these states, psi and phi, are eigenstates of H, which with same E. That means E is degenerate. So existence of an invariance property or existence of some symmetry is related to the degeneracy. Now I have made so basically this is two-way arrow, but I have only proved this arrow right now. But then this arrow has to be proved. Okay, but be assured that that is also something which we can prove. Physical symmetry sometimes may be difficult, but proving that such a symmetry exists is not very difficult. So that we will see as we go along. Okay, so this is in some sense the origin of the degeneracy. So there is some symmetry. For example, if you look at the isotropic cases that we have talked about, so x going to y, the Hamiltonian does not change. So x going to y is basically some kind of a rotation by 90 degrees of your coordinate system. So under that operation, under that symmetry operation, your Hamiltonian does not change. Okay, but if you have an isotropic case, then x going to y is not a symmetry of the system. So that means you are lowering the symmetry. Now, once you lower the symmetry, then the degeneracy gets lifted. So higher symmetries will have more degeneracy, and lower symmetries will have less degeneracy, or maybe there is no degeneracy. So that is the connection between the degeneracy and the symmetry of the system. Any other question?
So one question.
Yeah.
So when you showed the first example of degeneracy, you took two f functions, psi 2, 1 and psi 1, 2. So sir, like as a total wave function, the correspondent parts are different, but as a total wave function, they are similar if you write them down.
You are asking
Because
the
because
quantification.
they're like a multiplication of functions. So if we write 2 and 1 and 1 and 2,
Ah,
since they are like there's no issue of commutation there, so it's basically the same thing. So how can we differentiate given a
they,
total wave function?
no, they are not actually same because see, I think you are asking about um psi 1 comma 2 of x comma y and psi 2 comma 1 comma x comma y, right? About these two wave functions.
Yes, sir.
So this wave function is 2 by L sine pi by L into x and sine 2 pi by L into y, correct? And this wave function is 2 by L into sine 2 pi by L into x and sine pi by L into y. These two are two different functions, no,
So,
mathematically.
so we can differentiate between this x and y during this wave functions because
Yes.
it depends on our preference, right? So whatever we choose as x and y.
Yeah, but what I'm trying to say is, suppose if you are trying to plot this function, okay, I do not know if I'm, let me try my luck. Suppose let's say that you have x and y, okay. Now let's say I want to plot this function, okay. So now what happens? Along the x-axis, there is no node here, okay. So along the x, there is no node. So along the x, it will be like this. It will be like this. Whereas along the y, there is a node. That means it will actually come like this, go to 0 and then go down and then come like this. So you have to combine these two things in some three-dimensional plot, which if I draw, I think I myself will not understand. But what I want to tell you is that, see, one of the thing that we can imagine is that this tray in which you keep eggs, right? If you want to carry eggs, there is a tray, right? So it has those slots, correct? So this is like a slot. So now along the x, there is only one slot. Along the y, like you have two slots. I'm talking about, let's say,
Yes,
if you
sir.
talk about probabilities, along the y you have two slots. Along the x you have one slot. Now, in the other case, you have two slots along x and one slot along y. So wave function mathematically is different because wave function is a function of x comma y.
Okay, sir. Got it.
Yeah.
Thank you.
Okay. Any other question? Okay. Well, so let us look at. Okay. So I wanted to. Yeah. Okay. So let us look at. So this is with respect to both harmonic oscillator and Swan. Now we can talk about. We can talk about some problems of this type. For example, let's say that, okay, so maybe I just make one remark here. This is also related to, so suppose, let's say that I have XY plane. Okay, so this is with respect to, this remark is with respect to particle in a 2D box. Okay, particle in 2D box. Okay, so now let's say that I have a square box, a rectangular box. We have solved that problem, and we know that there's exact energy eigenvalues. Now you ask a question: if I have some box of some arbitrary size, arbitrary shape. Okay, so now this box is such that the particle is the potential is zero inside this box, inside the box, and infinity outside. Okay, suppose if you have this kind of a box, now you ask a question: can we solve this problem exactly? The answer is no. Or you can ask a question: for what kind of shapes can I solve this problem exactly? Barring square and rectangle, we have already seen. But you ask a question: what are the other shapes? Okay, so you can think of a circle. Okay, so if you have a perfectly kind of a disk, okay, so you can solve this problem of particle on a disk, problem. That means this is a circular region. Okay, uh, and there is a lot of work. In fact, you have some kind of a uh, particle particle in stadium. So they call these arbitrary shapes as stadia. So particle in a stadium kind of. So this is almost a research problem. So people are trying to look at energy eigenvalues of a particle in a stadium. Kind of a stadium will have a much better shape than what I have drawn, but then there are interesting aspects of these energy levels and energy. These are of course done by numerical methods. So usually this is done numerically uh, on a computer, and then try to understand how. I mean, what are the new features of this arbitrary shaped boxes? So I wanted to make this remark because even in this simplest case, the shape of the well is very important, and it's not it's not possible that you can do this problem exactly for any arbitrary shape. But when people try to look at them numerically, there are interesting observations. For example, this particle in a stadium is also related to some features that people study in what are called quantum chaos and things like that. Okay, so this is just to give you some kind of a pointer that some numerical work on these lines is very interesting, and it is um, almost at the research frontier level. Okay, so let us, having made this remark, so I think I think whatever Ritesh has asked earlier, we can. I wanted to see if the question is like this. That is, if you have a rectangle here, so can we have a potential in the rectangular well like this? That means this shape is like a rectangle. Okay, so this is
Triangles.
triangle. So this is a 2D shape. But then one can, I don't know if the question that he asked is whether in a one dimension itself we had talked about a potential well like this. I mean the particle in a box like this, and harmonic oscillator like this. But why can't we think of a potential well like this? It's like a triangular well. Okay, so
So
I
this only
you
asks,
asked
sir.
you
No, no,
asked
this
this
is
question.
whatever you told only asks.
Did you
That
ask
was
in
my
2D case or 1D case?
2D case, sir. 2D case.
2D case. Okay. Okay. So this is also another question which I think you can share some of your thoughts on this. So let's say V of X. So this is a harmonic oscillator, and this is, so this is a potential, triangular potential, you can call it.
Sir, we can inspect that using this power law protection, sir, like that triangular shape, that triangle shape we get. We can make changes in the power law and we can get that shape. So that was what I was thinking.
Yeah, yeah. But think of solving Schrodinger equation, then you will get more interesting insights. Okay, so these are some remarks, and so my remark about this is general particle in a stadium is an interesting problem which cannot be exactly solved, but then there are some ways of solving it numerically.
Sir, but I saw a problem where they have solved particle in a tetrahedral box. Like it was done by Mani sir and H.C. Verma sir. It is there. It's a paper is there. They have just
Yeah.
used basic arguments.
Yeah. So that is a three-dimensional generalization of this one.
Yeah.
Okay, so yeah, so that is true. So now let us look at a different set of problems. See, ultimately, the exercise that I am starting now will culminate in solving hydrogen atom problem. So our aim is to solve hydrogen atom. Okay, so this is our aim. But now we will try to proceed to that. Now, hydrogen atom problem has got a Hamiltonian like this. Hamiltonian is equal to, it's a three-dimensional problem. So px square, py square plus pz square by, usually we solve it with a reduced mass of proton and electron, which I will call test twice mu, and then the potential energy. The potential energy is minus E square divided by 4 pi epsilon naught into R. So this is our Hamiltonian. Okay. So by the look at the Hamiltonian, you may see that I have written px square, py square, pz square. So ideally, I should have written this R as square root of x square plus y square plus z square, right? So here R is equal to square root of x square plus y square plus z square. Now, since V depends only on R, since V depends only on R, okay, so it is convenient. It is convenient to work with spherical polar coordinates. Spherical polar coordinates, namely r, theta, and phi. Okay, so one of the important aspect here is that now I will write my Hamiltonian in this fashion: h bar square by 2m into del square, the Hamiltonian operator, minus e square by 4 pi epsilon naught into r, of course, in the position basis. So it is important, it is required to express this del square in r theta, in the derivatives of r theta. r theta by derivative. This is Laplacian, and Laplacian in terms of r theta. I am sure in electrodynamics also you require this, because in spherical symmetric problems, if you want to solve Laplace equation or Poisson equation in electrostatics, you require to use this. Now let me first write down. So this del square is equal to, in spherical polar coordinates, this is given as 1 by r square into del by del r into r square del by del r plus 1 by r square sine theta into dou by dou theta into sine theta dou by dou theta plus 1 by r square sine square theta dou square by dou phi square. So this is the expression for del square in spherical polar coordinates. Okay. Now, usually one can work this out, and mostly it is left as an exercise, and nobody does this exercise because it is a little hard. If somebody is leaving it as an exercise, very few people will do the exercise. Okay, so but I feel that every difficult thing you have to do it at least once. You don't have to do it again and again and again. But unless you do it, you will not appreciate the difficulties involved in this. Okay, so now what I will do is that I want to simplify this further, simplify this a bit. Okay, so let us consider a two-dimensional case. Okay, a two-dimensional case. That means here we are going to talk about plane polar coordinates.
Which means azimuthal symmetry, no, sir?
No, I'm just considering only one
I-
case, xy. Plane polar coordinates r, and we'll call it as theta. Okay, so that means this del square, which is written as del square by del x square plus del square by del y square in 2D, will now has to be written as del square in terms of in r theta. Okay, so let us try to do this. This is a simpler exercise than the previous one. So what we will do is that you know that polar coordinates, plane polar coordinates are defined like this. X is equal to r cos theta and y is equal to r sin theta. So that r is given by square root of x square plus y square, and theta is given by tan inverse of y by x. Okay. So I have to go from a Cartesian expression of del square to the plane polar coordinate expression del square. So that means every one of this del by del x, del by del y, I have to get in terms of. So I can write, so x is a function of r comma theta. So I can write down del by del x as del by del r into del r by del x plus del by del theta into del theta by del x. Now I have already written down this del r by del x and del theta. So let's try to get them here. So del r by del x is equal to 1 by 2 root of this into 2x. So 2 will cancel. So it is x by square root of x square plus y square, or I will simply call it as x by r. But x is equal to r cos theta, so r will cancel. So this will simply be equal to cos theta. Similarly, you write del r by del y, that is equal to y by r is equal to sine. Further, you ask what is del theta by del x. Del theta by del x is 1 by 1 plus y square by x square into minus 1 by x square. That is with respect to x. So this x square, when it goes up, it becomes, so this is equal to minus x square by x square plus y square into 1 by x square. So x square will cancel. And this is 1 by r square, right? Sorry, minus y by x square. Minus y by x square. So you have this y. So this is equal to minus r sine theta divided by r square, or this is equal to minus sine theta by r. Similarly, dou theta by dou y is equal to 1 by 1 plus y square by x square into 1 by x. So that gives you x divided by x square plus y square, which is equal to cos theta by r. So I can write this del by del x as dou r by dou x is cos theta. So this is cos theta into del by del r plus dou theta by dou x is minus sine theta by r into dou by dou. Similarly, so this is your dou by dou x. Similarly, we can write down del by del y is equal to del by del r into del r by del y plus del by del theta by del y. So that is equal to del r by del y we know is just sine theta, and del theta by del y I know is, so this is sine theta into dou by dou r plus cos theta by r into dou by dou. This is our del by del y. Okay, this is we have obtained for one of the first derivative. And what we have to get is, we have to get del square by del x square. That is equal to dou by dou x of dou by dou x of dou by dou x. That's what it is, right? So this you can write it in the following fashion. So this is equal to cos theta into dou by dou r minus sine theta by r into dou by dou theta into same quantity, cos theta dou by dou r minus sine theta by r into dou by dou theta. So now you can see that this will act on each one of this. So first thing is, it acts on cos square theta into dou square by dou r square. R and theta are independent, so this dou by dou r will not act on cos theta. And this will act on this one, So this will act on this one in two different ways. First thing is it will have plus cos theta sin theta divided by r square into dou by dou theta. That is, it is now acting on only r, plus minus sin theta by r into dou square by dou r dou theta. So that is a term like that. Then, so this is the action of this term on these two terms. Have three terms here. Now let's look at the action of this on this one. This will have two terms. Okay, first thing is this cos theta will become minus sin theta. That will be sine square theta. Sine square theta by r into dou square by dou theta dou r. Sorry, this is simply dou by dou r. Dou by dou r. And then minus sin theta cos theta, sin theta cos theta by r square or by r into dou square by dou theta dou r. Okay, these are the two terms. And then from here also you will have two terms. First thing is plus sine square theta by r square into del square by del theta square. Then minus sine theta cos theta by r square. Okay, so this is now differentiating. The sine theta will become cos theta by r square into dou by dou theta. Okay, so this is how you have hope I have done this correctly. So first is
Excuse me, sir.
cos square theta. Yeah,
So in the third term, there will be cos theta also, right?
in the third term, that is first term with
That
the
sine
first
theta by r dou square dou r dou theta. That term there should be cos theta also, right?
dou square. Yeah, there will be cos theta also. Yes, cos theta. Yeah, you are right. Yeah, so now you can see that the order of the differentiation is not important. So that is minus, and this one is science. Okay, so at least this term will cancel with this term. Okay, and then you have sine theta cos theta. Is there a sign change in this? Del square by del r del theta. Let us say this is minus cos theta sin theta by r dou square by dou square by dou r dou theta. Okay, then you have sin square theta minus sin theta cos theta by r dou square by dou theta sin square. Okay, so I think we have. So what is that remaining here is equal to cos square theta del square by del r square minus 2 sin theta cos theta by r into del square by del r del theta plus sin square theta by r into del by del r plus sin square theta by r square into del by del square by del theta square. So that is what is remaining. from our this. Okay, so now let us look at the next thing, del square by del y square. So del square by del y square is equal to, so del y is sine theta cos theta by r. So sine theta dou by dou r plus cos theta by r dou by dou theta into sine theta into dou by dou r plus cos theta by r into dou by dou theta. So you get this as sine square theta into dou square by dou r square, and this one will have minus, so that will be plus. So sine theta minus sine theta cos theta by r square into dou by dou theta. Okay, and then sine theta cos theta by r plus sine theta cos theta by r into dou square by dou r dou theta. Okay, so then we have plus sine theta cos theta by r into dou square dou theta dou r plus sine theta plus cos square theta by r into dou by dou r. Okay, there are two terms for this one acting on this. Then you have plus cos square theta by r square into dou by dou square by dou theta square plus cos theta becomes minus sine theta. So minus cos theta sine theta by r square into dou by dou minus 1 by r square. Sine theta into cos theta minus 1 by r square dou by dou. R square and this plus, and then here is sine theta cos theta. Oh, sorry. So this is also plus here. So this is also plus. So this will not cancel. So there will be plus 2 sine theta cos theta by r square, 2 sine theta cos theta by r square into dou by dou theta. That term will also be there. And here you get, so this will be, this term is minus and this term is minus. So this is minus 2 times that. This will cancel with this term. And Sin theta cos theta by r, this will be 2 times, that will cancel with this term. So this term plus this term will cancel with this term. So when you add these two things, so when you add del square by del x square plus del square by del y square, then you have cos square theta into del square by del r square plus sin square theta into del square by del r square. These two terms will give you del square by del r square. Cos square theta plus sin square theta is 1. In the same way, you have sin square theta by r into del by del r and cos square theta by r into del by del r. So that will give you plus 1 by r into del by del r, and sin square theta by r square into del square by del theta square, and cos square theta by r square into del square by del theta square. That will give you plus 1 by r square into del square by del theta square. Okay, so this is all other terms will get cancelled. So please carefully look at this, and you can see that the del square in plane polar coordinates will have this kind of a an expression. Okay, so now I want to give you an exercise. So this is something which is easy to do. So we want to get del square for 3D. Now del square in 3D is something like this: del square by del x square plus del square by del y square plus del square by del z square. So this is what it is. Now in spherical polar coordinates, we have something like this: x is equal to r sine theta cos phi, and y is equal to r sine theta sin phi, and z is equal to r cos theta. Okay, so this is what is our spherical polar coordinates. Now I want you to, so let us consider some xi is equal to r sin theta. Xi is equal to r sin theta. Then you know x is equal to xi cos phi and y is equal to xi sin phi. Okay. Now this is, so this part of this part of del square is a 2D thing, right? So we can write it as del square by del x square plus del square by del y square can be written as del square by del xi square plus 1 by xi into dou by dou psi plus 1 by xi square into del square by del phi square. From whatever we have written so far, we can write it like this. Correct? Now, that means my now del square is going to be equal to this del square by del xi square plus 1 by xi into del by del xi plus 1 by xi square into del square by del phi square. Okay. Now you can see that okay, plus this is up to this, right? Now I have del square by del z square plus del square by del z square. Now notice that what is your xi? Okay, you notice that your z is equal to r cos theta and xi is equal to r sin theta. So in terms of z and xi, this is again like plane polar coordinates, no? So that means this dou by dou square plus dou by dou z square, you can write it again using plane polar coordinates thing that we have written. That is, our del square is equal to, so you can write dou by dou r square plus 1 by r into dou by dou r plus 1 by r square into dou square by dou theta square. That is with respect to these two. Okay, so these two can be written in this fashion. Plus you have this plus 1 by xi. Xi is, of course, you know, so we have to write 1 by xi. 1 by xi is like 1 by r, right? 1 by dou by dou y here. Okay, so this is what it is, right? So that is equal to, you can write that using that, so you can write 1 by xi into dou by dou psi. So this part you can write plus 1 by xi square into dou square by dou phi square. So this part you can write because your dou by dou psi will be now equal to cos theta. I think it is dou by dou y is sin theta. Yes. So this is equal to sin theta into dou by dou r plus cos theta by r into dou by dou theta. So you substitute this one here and then simplify. Okay, you will get this expression that we have written down here. Okay, so this I just leave it as an exercise for you, so that you will. I don't want to take out that excitement of getting this like this. So what I am trying to show is the trick is that you just solve a plane polar coordinates and don't do anything. Use that result 2 times to get del square for the full 3-dimensional Laplace. So we'll continue to use this expression in the next class to solve problems of spherical symmetry, but you try to complete this derivation from here. Okay, so I will stop here if you have any questions.
Sir,
Yeah.
can we derive a relation to find degeneracy in 3D box like we got for harmonic oscillator?
Yeah, so this kind of a general relation for the degeneracy of any system, there is no guarantee that we will be able to do. For example, for box, for a harmonic oscillator, somehow it is kind of increasing for everything, but it is not so for other systems. For example, box, sometimes it will increase, sometimes it will decrease. Some states are non-degenerate. So I think it is not. It's not a regular variation, and hence it is not very easy to define that. I mean, find out that one.
Yes, sir. Otherwise, we have to count every time.
Correct.
Yes, sir. Sir, in the hydrogen atom, is the interaction energy of electron and nucleus is considered to find Hamiltonian?
Yes, that is the potential energy experienced by the electron.
Yes, sir. Sir, in the triangular problem, in 1D box, like one-dimensional, what Ritish has asked, can we use the phi equal to modulus of x as a potential energy,
Yes.
and then
Yeah.
find Hamiltonian?
Yeah, that's correct. So you can try solving Schrodinger equation for V is equal to modulus of x.
Yes, sir. Then we have to find Schrodinger.
Sir, but that will be a discontinuous at the second derivative, the modulus function, what you put.
Yeah,
Right?
I think that's not a problem. It's in the
Yeah, we can remove that. That is, Yeah, it is similar to Dirac delta potential, where we take out the first order, second order derivative. Once you've taught, I think it is possible.
Yeah. Actually, you discover that you will get some solution which is related to some special functions called Airy functions. If you solve that problem, but I want you to think in another direction. For example, you have been always solving these problems with coordinate basis. But for this problem, you try to solve this problem in momentum basis. Then your Schrodinger equation becomes a first order differential equation, which is easy to solve. Because potential is x, you will have d by dp for potential. Then that equation becomes a first order differential equation. It's easy to integrate that equation. So you can get a feeling of, okay, I have solved this exactly, but in the momentum basis. But now you want to bring that momentum basis wave function to position basis, then you have
Yes,
to do a
sir.
Fourier transform. And that integral you will not be able to solve. And it turns out that that becomes kind of a representation of these Airy functions.
So you mean this to solve for this triangle problem? So what you're telling us?
Yeah.
Thank you, sir.